Welcome back to our electronics course. In this lecture, we'll continue our analysis of the motion of the charged particle under a uniform magnetic field. We will solve the same problem that we solved in the lecture and the last lecture, in which we have a particle at the origin and we have a magnetic field in the direction of x. But now we will change a little bit the initial condition. One of the initial conditions of the last lecture is that v naught x is equal to 0. Here, in this problem, we will assume that v naught x is not equal to 0, is larger than 0. So the particle q at t equal to 0 has v naught y equal to 0, but has initial velocity in the direction of z not equal to 0 and another initial velocity in the direction of y. Or the direction of x, I'm sorry. We will start by the same equations we started with in the last lecture. Fm equal to q v cross b. Applying the cross product, we will get these two terms. And this force is equal to acceleration in the direction of x, acceleration in the direction of y, acceleration in the direction of z. Equating the terms in the direction of x here and here, y, z and z. For y and z, we will have the same two equations we got in the last lecture. Following these two equations, we will get the same set of equations for the Vz, Vy, and the displacement in z and the displacement y. So we have a circular motion in the yz plane. But how about the motion in the x direction? How we get this motion? Simply equate the term in the x direction here, which is 0, by the term in the direction in this left hand side, which is this term. So this term equal to 0, because there is no term in the direction of x. Integrating both sides, so Vx is equal to the integration of 0, which is constant, because the derivative of the constant is 0. At t equal to 0, Vx is equal to v naught x, not 0, like last time. So this constant is equal to v naught x. So Vx is equal to v naught x. What does this mean? This means that the particle will preserve its motion, its velocity in the direction of x. Because simply, the magnetic force does not affect this velocity. Because it has no component in the x direction, only in z and y direction. How about the displacement in x? X is equal to the integration of the velocity, which is constant v naught x. So it equal to v naught x t plus some constant, at t equal to 0, x equal to 0, so this constant is equal to 0. So x is equal to v naught x t, which is a uniform motion. Linear motion of the time in the direction of x. So in yz plane we have a circle, and in the x direction we have a uniform motion that increases linearly with time. So in overall we have something called helix, uniform helix or spring. What does this helix or spring? Simply, we have here the particle q, it will move along this path until it reaches, after one cycle, it will reach the x-axis again. But not at the origin, like in the last slide, it will make a circle, no. At some distance here. In the second cycle, we start from here, move along some circular path, but in 3 dimensions, and after another period, we will reach x-axis again. Because this is a uniform helix, this distance from this point to this point is equal to this distance from this point to this point. And of course, this will continue infinitely in the direction of x. If we look from the x-axis into the y-z plane, we will have the same circle we have proved in the last slide, with center at z equal to 0 and y equal to v naught z over omega, and the radius equal to v naught z over